Hello everyone, and welcome back to a new video in programming the Finite Element Method using MATLAB. In this video, we're going to tackle the last function that is missing in our equivalent nodal load calculation, which is dealing with a trapezoidal moment, which means if I apply a linearly changing moment on a bar. Now, before I start, I want to give the typical reminders that this is part of the Finite Element Method series and that it's also part of its own programming series, both playlists linked on the top right. Furthermore, I want to mention that the entire source code is available to my dear channel members. However, if you are not a channel member, then don't worry, because every single line of code will be written in front of you. You can write along and you will have the exact same code as mine. So with that being said, and without further ado, sit back, relax, and enjoy the show. Okay, so now it's time for the trapezoidal moment. Also time for our derivation. As I said before, I'm using MATLAB 2017 for my derivation because my 2024 MATLAB doesn't have the symbolic math toolbox. The problem in the 2017 MATLAB is that it doesn't have the dark mode, meaning that you will see a sudden shift in the brightness. And here goes. So that's MATLAB 2017 without the dark mode. Now, I've done this before in the derivation with the symbolic math. Here, things are very similar with a one small difference. You see, instead of using this for our derivation, we are going to use the derivative. Look, what is the virtual work method? The idea behind it is as follows. The nodal force multiplied by the nodal displacement is going to equal the distributed force multiplied by the displacement field. And the displacement field basically can be substituted by saying summation, the shape functions multiplied by the nodal displacements. So you can see where this is going. F in this case equals displacement field. Oh, sorry, there's an integration here and there's an integration here because of variable. It's not constant. So here, now and these I can take out, which means integration distributed force with n, and the sum goes out. So I just did a pseudo math explanation for the entire virtual work thing. It's more complicated than this, but that's only a small explanation. Now, why do I do this? Because similar to force, I can use moments here. The moments here are going to be affected, same thing, by the integration of distributed force multiplied by the derivative of the shape functions. Why? Because in the get-go, when you want to derive it, it's going to be moment multiplied by nodal rotations this time. Now, the same derivation follows. However, we have a rotation field now. Now, this is basically the derivative of displacement. And that's why suddenly we integrate not the shape functions, but the derivative of the shape functions. Now, I will show this to you in action here. Let's say in symbolic, I declare sims f. Do I have an f here? No, so sims f, and now I declare f equals x, for example, square minus 5x, for example, okay? You can easily do a differential by saying df, in this case, equals differentiate. You put in the equation f, and you put in the variable that you're gonna differentiate for. So if I say x here and push the enter key, you can see that it gives you the derivative exactly as you would do by hand. So I told you, this sim stuff is ridiculously OP, and we're going to use that basically. So what we're going to do is we are going to copy this entire thing, which we did, by the way, and before we multiply, we must derive. So we derive the shape function with respect to x. Let me try that very quickly. So diff, let me see n1 first of all. It's this equation. Now differentiate n1 with respect to x, and let's see. Yeah, this is going to be 6. That's going to be 6. Yep, I think he does that. Okay, so everything seems to be fine. We can just call in diff for each one of those shape functions, and we're going to do that with respect to x because we want to find the work of the moment, which needs the rotation. So instead of the shape functions, I can differentiate to find the rotations. So now I need to paste this every time here. I copy this one. I pasted all over the place. I copy this entire thing, paste it here and here, and copy this entire thing, paste it here and here. Fantastic. Now those should give me the equations for Q1 to Q4 for when I have moment. So, well, let's run F5. And the equations are there. The only thing I have to do is to fish them out. So here I will put this for shears, and this for moments. Disclaimer, they are not yet tested, those equations. We shall test them later during the benchmarking. So here I would say Q1 equals, Q2 equals, Q3 equals, and Q4 equals. Just gonna copy paste those equations. Fantastic. And those are humongous equations, by the way. Now, once again, there is gonna be a shift in the brightness. We are going back to the dark mode. Now here in the, I forgot to declare this one, right? Did I declare a function? I did not even declare a function. Okay, fine, this is easy. I just copy this shear thing and paste it. It's out of indentation, so Control-I puts it back. Here, this is called trapezoidal moment. Now the arrows should subside, and they did subside. So far, so good. And here, the A is defined, the B is defined. The only thing I have to do is to copy my Q's that I have got, paste them here, just Control-I them and uncomment them. So I'll just take this and uncomment. Fantastic. Now those are my Q's. Were they tested? No. Do I trust them? Also no. I want to test it out first. I'm kind of putting my trust in MATLAB's Symbolic Math Toolbox, but there is no better way of checking things out with except a good old debugging session. So that's a rather shorter video. We have utilized the Symbolic Math Toolbox quite well, and we have finalized the entire equivalent nodal load calculation for the distributed and for the concentrated. And oh boy, was this draining. But we succeeded because there is no other option. We have to succeed. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a finally finished sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve. For that, I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.